Looks good.
Oh, do we want my video or not? Probably not, distracting. Okay, so this is a talk. I was invited to the Penrose conference in Red Lodge, Montana, and that was to actually see the Stillwater mine. And we got a field trip and got to go underground at Stillwater, which is the Stillwater mine, as in Stillwater, Sabanya. So it was very exciting because it was just before Sabanya bought Stillwater. And talking to the employees there, it was really, really an interesting time. They have quite a number of women geologists that are very active on social media and share a lot about mining at the site. So I'm going to speak about large and small scale geophysical investigations of the Bushveld, and I'll hint at some of the more recent work also. These are some of my co-authors. Carol Finn is at the USGS in Boulder, Colorado. And I think the rest of these people you probably know. Oboni Sapato's now at Anglo American. And Trond is one of our colleagues that we've worked with for many years in Norway. Sean Letts is now in Vancouver, and Grant Cawthorne has sort of retired, but he's still around quite a bit. Let's see, page down, is that gonna work? Okay, so I'm going to break this into three kind of sections. The first bit will be talking about cyclicity. The next bit will talk about connectivity. And the third will talk about some paleomagnetic insights and where we're going with some of those. Now, as always, I'm a big fan of physical properties. And when I started work on the Bushveld Complex, there were only about 50 published density measurements of the Bushveld Complex. And as part of my PhD, I wanted to do some gravity modeling of the Bushveld Complex. And I thought, geez, for something that's 400 kilometers across and 9 kilometers deep, and covers this huge area, why are there only 50 measurements published? Well, a lot of the data was tied up in corporate databases, but there was this borehole, the Bellevue borehole in the northern limb of the Bushveld Complex, and the core was at the Council for Geoscience, and it really hadn't been studied too well, and very little had been published on it. So we decided as part of our work to collect physical property data from the core from this borehole. And this is a nearly 3 kilometer deep borehole, single borehole into the Bushveld. And you can see down here in the bottom left, there's a Toyota Bucky for scale. This is quite an enormous rig. And this was drilled back in the late 1980s. And it's a research borehole that was actually funded by the Council for Geoscience. So it was all part of a research program. So where was that located? Well, this is the kind of standard map I use for the Bushveld. The green are the Rustenburg layered sweet rocks, which are outcropping. And we can see the northern limb here. I just want to go down and find my little laser pointer. Oops. Let's see, where is it? No, that was not a good idea. Shoot. Where is the laser pointer? There we go. There, sorry about that. Okay, so here's the location of the Bellevue borehole. It was actually collared in the granites, and then these green rocks are dipping to the east, or sorry, dipping to the west. So the green is outcropping here and the rocks are underneath. Probably we propose they're actually all the way over to approximately this location. And the Bellevue borehole goes through the granites, through a large amount of the upper zone, well, all of the upper zone and into the main zone. So this is its location. You're probably familiar with the Steelport Fault and some of the mines over here that we have worked on in the past for our field schools. And many of you may be working over here on some of the mines over in this area also. So what does it look like in cross section? Well, if we see here are the granites. There's a big dolerite sill that outcrops to the north and south and that is intersected in the borehole. And underneath that, dipping to the west, sorry about that, dipping to the west is the upper zone, and then the main zone underneath that. And in cross section, this is what it looks like. We've got the Bellevue borehole collared in the granites. It goes through the entire upper zone and about a third of the way through the main zone. And we think of this as a stratigraphy in the Bushveld. We often talk about it as a stratigraphy, even though it's a igneous, large igneous province. We can pull up here and see there's a gap between the stratigraphy of what we find in Bellevue and what we find in the moored copy borehole, which was a borehole drilled by Anglo-American and provided to some of our other colleagues. So what does 3 kilometers of borehole core look like? Well, this is just 2 kilometers, and this is the National Core Library at the Council for Geoscience. This is an amazing facility, and we really must try to get everybody up there to have a visit. It's absolutely a fantastic place to work. At most core sheds, you end up working outside in the hot sun, and it's really miserable conditions. But the National Core Library actually has space for you to be able to lay out 2 kilometers, even 3 kilometers of core. What we did was we captured 109,000 susceptibility measurements and approximately 2,200 density measurements on this core. The 109,000 susceptibility measurements were largely measured by employees of the Council for Geoscience at the time the core was drilled. And the decision was made not to geophysically log, but to have people measure the core samples because the cost ended up being the same, but you could keep 2 people employed and not fire them by actually having them do the work by hand, as opposed to sending a probe down the borehole and spending all the money on that. So that was one of the justifications for doing that work by hand. And they wrote down in 10 books that are about 1.5 inches thick each, a measurement on the core for susceptibility every 2 centimeters. And this means the core has been very well characterized by susceptibility. Now, unfortunately, those books were all handwritten and sitting on a shelf when we started this project. And if you want to know who the hero is, it was Lou Ashwell, who typed in almost all 109,000 measurements into a spreadsheet that is now available. So it turns out they only did 2/3 of the borehole, and we actually completed the last third, but we were very lucky because of the improvements in technology. We were able to collect those data directly to a computer and merge those spreadsheets. So what does the data look like? Well, the first thing to do when looking at core is to make a lithology log. So here we have quite a fairly detailed lithology log. And of course, this is in a, well, it's actually in a CorelDRAW file, but you can look at this in some detail. And everything thicker than 2 or 3 centimeters has been logged in fair detail. And we see in the upper zone, we have magnetite rocks or rocks rich in magnetite. And then we have this sharp cutoff with this red line here, where we have the main zone below that. And the main zone is gabbros, gabbronorites, melanorites, et cetera, et cetera. So all these rocks that are made up of plagioclase, pyroxene, and a few other minor constituents, 2 types of pyroxene. So the rocks are fairly simple here. We also have little layers of granite that we can see. The pink are granite. And we have this thick sill that we saw on the map originally that actually shows up in the borehole about here. And the susceptibility data are shown here, and we can see a very sharp cutoff. And in fact, geophysically, that is what we use to define the break between the main zone and the upper zone. Why? Because it's very easy to identify in the field. I may not be able to see the magnetite necessarily, but boy, it sure starts, and you can see it with a susceptibility meter or even a little pen magnet right at that boundary between the main zone and the upper zone. The density data were such a surprise. Here's our density data. We've got density on the bottom here from 2.5 to above 4. And this is with depth. So the surface is here at the top, and we're going down the borehole. This is the upper zone here and the main zone down here. And when I first saw these data, I was just completely shocked, because we have units over and over of density increasing upwards. All what I was expecting was kind of a consistent density through here, maybe some variations as we changed rock types a little bit, but I certainly was not expecting such a cyclical pattern of these upward increasing density. So this really doesn't make sense when you glance at it. You have this layer that seems to have very sharp boundaries on the top and the bottom, and the dense material is at the top. How does that happen? You would really expect dense material to sink to the bottom of the layer. And in many, many intrusions, we do see that. We actually see density is higher at the bottom and lower at the top of a layer. So this was really, really intriguing. It's a little less clear in the upper zone. And in fact, in the upper zone, we see a much more classic layer. So this layer, which is approximately the same size as some of the layers in the main zone, actually, although it has a big component of granite there, which comes in much later, we see denser material at the bottom of the layer and less dense material at the top. So this is a big change in how the layering is behaving. Another important point is this scale of layering had never before been observed or documented in the Bushveld. And one of the things I did was look at the wavelet signal of this and document that it's basically 100 to 150 meters of thickness for each layer in the Bushveld, or in this main zone and upper zone. And Oboni Sapato, who was my MSc student many years ago, he actually looked at this in a number of other boreholes around the Bushveld. And it wasn't as clear cut, but we did see similar layering. He was looking at the western and the eastern limb, and we don't have as many deep, or we don't have such nice deep boreholes. So he was looking over shorter intervals, but we found several places where, again, we had this layering, but in his case, the layering would sometimes be increasing upwards and sometimes be decreasing upwards. So a very, very interesting MSc by Oboni. One of the things we like to do is quality control. And so this is a really nice way to plot your physical property data, where you can actually plot 3 different properties. The lithology, you can color code that. So that gives you kind of one field that you're plotting, and the magnetic susceptibility here in SI units, and the density. And what you expect to see is much more variation in magnetic susceptibility than density, obviously, because this is orders of magnitude more spread in the susceptibility values than we have in the density values. But you also expect to see clusters of data. We expect the high susceptibilities to be these purple rocks, the magnetite norites. If we're getting yellows up here, which are northicites, they are probably misidentified. So this is a great way to check your lithology log with the physical properties, which are actual measurements, so they're not biased. You can actually check if your lithologies have been correctly identified by where the physical properties plot. And if you have suspicious values like this anorthosite over here with quite a high density and a very high susceptibility, that looks like it might be wrong. And you can go into your database and double check with the rock in the core yard to make sure that these are being plotted correctly. And so this is a nice example of a quality control check, but it also shows us some interesting fields. One thing we noticed right away was it seems like the granites, which are late stage, the granites cross-cut throughout the Bushveld, and they come in late in the Bushveld. The granites, several of which are probably too high density over here. These are probably misidentified again. But they seem to have 2 different clusters. And when I looked at these in some detail, what I found is that the higher susceptibility granites were actually in the main zone, and the lower susceptibility granites were in the upper zone, which is kind of not what you would think. And it kind of makes you wonder what's going on. We haven't really thought too much about that, most of the Bushveld geologists that I work with are very uninterested in these granites, but I think they're actually kind of telling us quite a bit. And so I'm keen to work on them some more. So another thing I did was compile a whole bunch of histograms. I took out each lithology and I looked at the histogram of the density and susceptibility for it. And this gave us an idea to see if we really had statistically significant numbers of measurements for, to be able to really say whether or not, well, to be able to give a mean density for each of the different lithologies and quantify what the overall density of the rocks we had measured was. We can see some very nice histograms here. For example, the gabbro-norites are fairly well distributed. There's a lot more spread in the magnetite leucogabbros and in the magnetite gabbro-norites because these have varying amounts of magnetite. In fact, the magnetite gets so rich that it actually affects the density dramatically. So this is one of the rare cases in the world where magnetite, which is usually a minor constituent in a rock, actually is so prevalent in some of these rocks that it affects the physical properties. We see a long tail on the anorthosites, and the pyroxenites are fairly well spread out. So when I combine all the cumulate rocks, which are all the rocks associated with the Bushveld, this does not include the dolerite sill, which comes along at a much later date, and it also excludes the granites. We see that we get a fairly high average density or mean density for the Bushveld rocks, certainly much higher than the commonly used 2.67 value that we frequently use for crustal density. So this gave me my first inclination that the average crustal or the average density of the Bushveld complex was significantly higher than the average crustal density. And I have actual data to prove it. And the rocks below the main zone and upper zone are also quite a bit denser. They're in the critical zone, for example, you have more pyroxenites and heavier rocks. So we can use this as kind of a minimum density for our gravity modeling, and we have actual data that we can cite. So I mentioned earlier about these layers that we see in the density data. And so that got, of course, Gordon was right down the hallway, so wavelets were the thing at the time. So of course I applied wavelet analysis to these density data to see if we could really pull out some of the layering or the wavelengths in the layering that we're seeing. And sure enough, we can see that there's a fairly dominant wavelength in the 100 to 150 wavelength scale, but there's also a whole series of shorter wavelengths that seem to be present in the data. And it's very difficult in the upper zone because the susceptibilities are, the densities are dramatically influenced by the layering of the susceptibility or the layering of the magnetite. And because our measurements are about 1 meter to 1.5 meters apart in the upper zone, we haven't captured all that fine detail of the magnetite layering. So although the broader scale increases and decreases in density are correct, we haven't really captured all the layering at the finer scale because of our sampling interval. That we have with the susceptibilities, but certainly not with the density at this in the upper zone. But in the main zone, and the main zone starts roughly about here and goes down to a depth of almost 3,000 meters, we can look how much stronger this wavelength signal is and how it really is about 150 meters, and then it tails off to a slightly shorter wavelength at the bottom. And we can see this layering over and over and over again. And it's almost always density increasing upwards. We also looked at how the statistics varied down the borehole. This was kind of a neat image we called the Y image, or windowed histogram image, where we take a window of data of about, say, 50 to 100 data points, And we do a histogram horizontally, where red is the highest reading in the histogram, so the highest number of points. And so you this kind of tracks the density down the borehole and gives you an idea of how the statistics change as we go down the borehole. In some places we have a broad spread of values, and in other places we have a very narrow range. So quite an innovative plot from Gordon. Now this is something that also intrigued me, that I can't seem to get my geology colleagues interested in, but we see here, I've marked in red every single one of these layers that I've considered fairly well defined. Obviously I've marked them in red, so you see them a lot better. But every single one of these has density increasing upwards over a fairly long interval. And what really intrigued me is that most of these have a granite bracketing them. Now, to me, this says there's a rheological boundary there that could allow the granites to come in at a later date. So to me, this looks like the layering is defined top and bottom by a layer of granite. However, in the work that Ben Hayes and Lou worked on, and I'm also on the paper about the interpretation of this, we've actually interpreted it a little bit differently because of some of the isotope evidence. And we think that a pulse comes in and then drains down into the layer below it. And that gives us these higher density components tagged on to a lower density component from the previous layer. Why this allows the granites to so consistently intrude through these at these specific locations, they're definitely not random. They're definitely at the top or the bottom of each one of these layers. Why that happens, we haven't really solved that issue. I think there may be another mechanism for the layering, but I haven't been able to convince any of the geologists of it. So we're still working on that. We're still arguing about it. So there's another borehole in the eastern Bushveld, the so-called Ellen Wilson borehole that was drilled by Anglo-American. And this one is also fairly deep. It goes from 0 down to almost 1,300 meters. And in this one, again, we see patches of layering. So it's not as clear cut, but we do see over again these layers. Steph, are you trying to say something? No, okay. So
no,
we do.
all good. Sorry.
No. It sounded like someone was trying to break in. I'm not watching my time very well here.
So. It's 11:30. I'll stop you at 12, and we can.
Oh yeah, no, I'll be done by then. Don't worry.
Okay, cool.
So we can see changes in the layering throughout this borehole. It's not as clear cut as it was in the Bellevue borehole, but this one in the eastern Bushveld, and at the time I wasn't allowed to show the location of it, but we do have the location, and these data were collected with borehole geophysics, so they're much more dense. There's much more measurements down this borehole than the previous one. So again, this adds to our database of knowledge of the density values in the Bushveld. And yeah. Okay, and so this is some of the work from Oboni Sapato, and he also looked at, this is one of his boreholes, again on the eastern limb from Anglo-American, and you can see several episodes of density increasing as we go up the borehole. So this is the top of the borehole, 0 at the surface, and this borehole is only about 700 meters long, so it's not nearly as long as some of the others. And you see a few instances where there's clear-cut layering, but you also, he didn't identify it, but it's definitely there. There's instances where the layering goes the other way. And we never really completely solved that question. And it's one of the things we're very interested in looking at again. You don't really see it in the lithology itself, the layering, the change in the physical properties doesn't really show up. So these physical properties are really quite important. So this is the setup at the moored copy borehole, which, if you remember from the very beginning, is to the east of the Bellevue borehole, and it continues on through the main pond and into the floor rocks beneath the Bushveld complex. This is the wireline logging setup. The borehole was logged with geophysical instruments and not by hand. We do have, well, we have had access to the core. And in fact, Freddie Rolofsa, who's at University of Free State, did a lot of work on moored copy. So if we put them together in a stratigraphic column, we can see the Bellevue core here coming down all the way to just before 3,000. And then there's a gap in the data. And then the lithologies of the moored copy continue down to almost 5,000 meters. So essentially the total thickness of the here in this area is about 5,000 meters. We see here the data we collected by hand, density data for Bellevue here at the top. And
Steph, could you perhaps mute Emily?
Oh, sorry. Oh, wait. I thought I had, sorry.
No problem. Thanks, Ray. And here we see the much richer data set we get, or much more data we get from the density measurements in the moored copy borehole, which were collected with the instrument. And you see a lot more spread in the data too. There are issues with some of these data, and we have to look at them very, very carefully. We see the same in the susceptibility. There's a lot of data dropouts in the log or in the magnetic susceptibility measurements from the downhole geophysical data. And that's something we're still looking at and trying to understand more fully. These are the data we collected with the susceptibility meter. These are the 109,000 data points that were typed in, and another 40,000 that we collected ourselves up here at the top. So just a summary of the learnings from the density and cyclicity. The inspiration for the project was to collect density data for gravity modeling. We discovered a scale of layering not previously documented of about 150 meters, especially in the main zone, where density increases upwards, which is very unusual in a magma or mush environment. You expect heavier elements of the mush or the magma to sink to the bottom. The statistics change significantly as you go along the core. That's the windowed histogram image that we talked about. And there's regions of intense sublayering that are observed, which we don't fully understand. That could be small scale convection of some kind or sorting happening in the layering itself. And the density cycles, we have interpreted these as being related to emplacement, that these these layers at 150 meters are pervasive throughout the Bushveld complex, as we've seen from Oboni Zapato's work. And we see that also in the Wilson borehole. And we feel that these are pulses of magma coming in at that scale of 150 meters thick that are then solidifying over time. This is to remind me, we're moving on to a new section. That's one of my Dalmatians on the spotted and northern site in the Eastern Bushveld complex. So this section, now that I had some density data that I was fairly confident in, I could start looking at the gravity modeling of the Bushveld complex. So this section will talk about connectivity, cooling, and paleomagnetism. Now, the Bushveld complex is interesting. It shows up. This is the gravity data of Southern Africa. It's a very nice compilation of data from several countries. And I've imaged it here with minus 210. This is the Bouguer gravity. So it goes from minus 210 up to plus 75. And this is the effect of the crust thinning as we get to the coast. because of course we're approaching the much denser, the continental crust is thinning, so the low density granitic type crust is thinning, and we're approaching the much denser but thinner oceanic crust, which has a higher gravity signal. And I'd like to point out two features here. We can see a whole bunch of features. I mean, for example, there's the vredefort impact structure. Even the Colesberg lineament kind of shows up in the gravity a little bit, and the edge of the craton shows up. But the two features I want to point out the most are the Bushveld complex here. You can outline it, you can see the gravity, and it's a gravity high. As we said, the density data shows us that the gravity or the rocks are more dense than the surrounding rocks. And so the background is kind of this light to darkish blue color. That was what we would call our background of our gravity anomaly. And the other feature is Trompsberg. We notice the Trompsberg intrusion here, which is buried beneath a kilometer of crust. It's been drilled, so we know how deep it is. And it's been buried beneath a kilometer of crust. And in spite of it being so far away from the surface, it's still got a higher gravity signature than the Bushveld complex. So keep that in mind. The Bushveld is actually outcropping, but it has an amplitude of signal, of gravity signal, that's lower than what the Trompsberg has, even though the Trompsberg's buried a kilometer beneath the crust. So what does the Bushveld look like? We have, here we have the western limb and the eastern limb, and these are the two limbs that were traditionally studied. This is the southern or Bethel limb, and then here's the northern limb, and here's approximately where that borehole was. So there's the western and eastern limbs, which we'll look at a cross section now through the crust. So here's our western limb, and here's our eastern limb. And this isn't the first image, but it's quite a nice one that kind of explains the thinking of the time back when Alex Dutoy was working on this. And this is from his book, The Geology of South Africa. And it shows the western limb of the Bushveld outcropping, and then the eastern limb of the Bushveld outcropping. And then it hypothesizes that the Bushveld is connected at depth from west to east, and that the granites on surface kind of cut through. So it's not perfectly connected. There's certainly things interrupting it that we don't fully understand, and there's dikes and things cross-cutting it. But in general, the rocks that are on the west are the same as the rocks that are on the east, and they're connected at depth. And this model was called the Lopalith model. So it says the Bushveld Lopalith from east, well, it goes from west to east, of nearly 300 miles, which is about 400 kilometers. And if you think about it, you know, there's platinum outcropping here, there's platinum outcropping here, there sure should be platinum all through the center of the Bushveld complex. So let's look at another feature, which we're also working on. To the west of this is the Malopo Farms complex, which is the same age as the Bushveld complex. It's got to be part of the same intrusive system. It's the same age. It's connected along this so-called TML, or the Tabazimbi-Murchison lineament or fault zone. Has different names along it, but in this paper by Cawthorne and Walraven, it's been labeled the TML. And this turns out to be a very important feature we'll talk about later in our work, where we think actually this provided access for the magma from the magma chamber to the northern and southern kind of pockets of the Bushveld and the Malopo Farms complex. So anywhere else on the Earth, Malopo Farm complex would be studied like crazy, but it's undercover mostly in the Kalahari sands are covering the Malopo Farms complex, and it's small compared to the Bushveld. So everybody studies the Bushveld because it's more accessible. There's outcrop and there's tons of platinum in it. There's been a bit of exploration. In fact, there's ongoing exploration in the Malopo Farms complex, but it's clearly not as well mineralized, or certainly the mineralization has not been as easy to find as it has been in the Bushveld. So in 1959, when the gravity survey of South Africa was starting to be compiled, Cousins, who was a physicist, had a look at the gravity data, and he set the scene for the next, well, until the 1990s, he set the scene for the interpretation of the Bushveld. Now, I remember when I arrived in the country in 1990, I asked people about the gravity and the Bushveld, and the set response I got from everyone I spoke to was, the geophysics proves that the Bushveld is not connected. It has to be separate lobes, and the geophysics proves this. And this comes from this paper of Cousins in 1959. And apparently he was a very powerful speaker and very persuasive, and would argue with anyone who argued against him. And we can see this in some of the literature. Back in the old days, they used to put commentaries in the journals about meetings and debates that took place in the meetings. And those are really quite rich readings if you go back to the old transactions of the Geological Society of South Africa. They're actually a lot of fun to read, because almost every single paper had a commentary after it and a reply to the commentary, which could get quite heated. So anyways, Cousins was very persuasive in his arguments about the Bushveld not being connected. And the argument goes like this. Here are the gravity data going from west to east in the Bushveld. Here's the town of Northam, and we're going west to east, and you can see the little bit of outcrop he's indicated here. And we can see the gravity anomaly in milligauss goes from 0 up to 80 milligauss, okay? So that's quite a big gravity anomaly, and it's the same size in the east. And note that it goes down to almost 0 in the center. This is a critical piece of information. And it's also 0 on the east side, and this would pan out to be 0 on the west side. So we've got Bushveld granites, we've got norite zone, we've got the Transvaal underneath it. So these are the gravity data that he was working with. And what he did is he said, okay, well, if we have a lopolith, let's make a very, very, very simple model, because of course we have to calculate every single point by hand. Let's make a very simple model of the Bushveld. So this layer that you see here is meant to represent the lopolith model of the Bushveld. Here are the granites, and here is the Transvaal underneath. And we see we've got a problem. We can reproduce the amplitude of the gravity anomaly. There's no scale here, but this is meant to be approximately the same amplitude as the actual data. But in the middle, the gravity values do not come back to 0. They do not come back to background as the actual gravity does. So this calculated gravity profile is what Cousins used to say you cannot have a connection through the center, because if you do, the gravity values will be elevated in the center. Therefore, he suggested a geological model whereby you have 2 separate intrusions with no connection in the middle as the preferred model for interpreting the gravity data. So you have a sharp peak here and a sharp peak here, and nothing in between. And most importantly, no platinum in between. So this is the separate intrusion model, and you would expect to have a feeder zone directly underneath kind of the peak, is what he implied. And you can see the approximate scale here. So these are well separated intrusions. There's no mistaking these 2 different models. And so that's just to highlight it in kind of watermelon colors, as we've done in our chapter in the book. Ray kindly asked us to have a chapter in. And you can see how the granites get thicker, and even though they're quite low density, they do bring the values down, but not enough to bring it back to background. And there was a lot of debate about this. I mean, this is a paper that came out in '76, Van der Merwe. We didn't have very good age dates on a lot of these intrusions. So there was even some speculation about the the Great Dike up in Zimbabwe somehow being connected with the northern lobe of the Bushveld and connect on through to the Trumpsburg, which, all of these dates on this image are wrong because they're quite old dates. There were fractures proposed that all this stuff intruded along, and you've got many different lineaments. So there was a lot of work, trying to connect these things. We now know that the age dates are very, very, very distinct. Even here, they're starting to separate quite a bit. But it's interesting, are these fractures important and how can we look at these? And I think that's where a lot of the seismic data that Musa has is going to become really important, is to try to understand which of these fracture zones are actually really deep-seated, which are actually suture zones in the early accumulation of the continental crust. So here's a look of another model by Van der Merwe in the northern lobe. So just to put you in the picture, here's Potgietersrus, here's the northern lobe going up. Here's this little Terra Nova zone up here. And you'd like to say, geez, well, how far west does this Bushveld go? Does it go all the way over here? Do we have possible platinum resources all the way under this area? And you can see here, Van der Merwe's gravity modeling shows that the inferred limit of the layered sequence only extends about 50 kilometers at the most. This is the scale bar here. This is 0. This is 50 kilometers. So at most, he allows for the layered mafic rocks to extend 50 kilometers into the interior, and definitely not 300 kilometers further west. So this is just the blow up of that. So you can see this. Sorry, this is the Villanora, not Terra Nova. I don't know where that came from. The Villanora lobe up here on the north. And the inferred limits of the layered sequence here, very, very close to the actual outcrop of the layered mafic intrusion. And he simply modeled this because, of course, there weren't really computer programs. It wasn't so easy to model in 70, well, this is now 87. This is Duplessis and Klavec. And they were modeling a very simple triangular structure. This is, again, just a simplistic model. And this model also supported the previous model that said the northern lobe only extends 50 kilometers into the west from the actual outcrop. So they're just looking at this bit of the gravity data. And Meyer and De Beer looked at this using not just gravity, but they also used deep electrical soundings. And they agreed that it had to be well separated. They moved away from the kind of separate intrusions and they went with a dipping sheet model. So the number 4 and 5 here, the gray is the Rustenburg layered suite, the way Meyer and De Beer modeled it. And they got a paper on this in Nature stating that the Bushveld was not connected through the center. So this was quite a big piece of evidence. And I re-looked at the deep sounding data that they used in my thesis and concluded that they're just at the edge of resolution, and there are some actual conductors in the transval underneath that could be confusing to interpret. So although they gave a very clear interpretation, it's not as clear cut as it might seem from this simple model. So I decided, this is just so you can see it a bit better. You can see this now so-called dipping sheet model of the Bushveld complex, which is used to argue there is no layered mafic intrusion in the middle. There's no main critical or lower zones of the Rustenburg layered suite in the central part of the Bushveld. And in fact, there's a small alkaline complex that they've attributed this small gravity anomaly in the center to, which doesn't sit well with me. We don't have any density measurements of this alkaline complex, but they're usually lower density than mafic rocks, although they're sitting in granites. So we would have to actually measure these densities, but that's quite a substantial gravity anomaly. Just please note, if you do read this paper and you do use this diagram, be very, very careful. The residual Bouguer anomaly in this case is given in gravity units, which are different from milligauss. They're an order of magnitude larger. So always, always, always check your units. And this is the first diagram we see where the depth in the crust has been explicitly given. They've been very careful to give a nice depth scale in kilometers, and they're modeling down to a depth of 15 kilometers. Now I want you to look carefully. This is 400 kilometers west to east and 15 kilometers in depth. That means this entire depth, if these two were to go to scale, would be only down to this level. Okay, so this is 15 kilometers and this is 400 kilometers. And this is typical of the vertical exaggeration we often use in the Bushveld complex. But we really need to keep in mind that this is barely dipping. The Bushveld looks more like a dinner plate than any kind of steeply dipping structure. So please keep that in mind when you're working on these data. So I decided, well, during the Cap Ball project, I was privileged to go to MIT as a visiting researcher, and I spent a lot of time there. And I was staring at this image on my screen. I had created this image and looking at the gravity data and really trying to think about these ideas that the cousins had put forward, that there was no way this thing could be connected. And I was actually sitting next to Tony Watts, who wrote the book on isostasy and crustal flexure. He basically invented that whole field by looking at seamounts in the ocean and how they flex the crust, the oceanic crust. And I was looking at this and saying, oh my gosh, this looks like crustal flexure to me. And I turned to him and I was very intimidated by him because he's a very famous geoscientist and I'm very impressed with all of his work. And I finally got up my courage and turned to him and said, does this look like flexure? And of course he had no idea what I was talking about. And we had a quick chat and he encouraged me greatly. And then he said, I have to leave in 10 minutes to catch my airplane back to the UK. So I've since made contact with him and we're now colleagues, I would say. He works at Oxford, and when I go visit Oxford, I spend quite a bit of time chatting with him about different projects. So he really encouraged me to look at this as a case of crustal flexure, and that's what I want to look at here. So just to remind you, the scale here is from minus 210 milligauss are these deep purples, and 0 milligauss are the reds, which are really only seen up here in this Patitas Rus area, which will become important later. So the first thing we always do when we're looking at data and previous work is we try to reproduce the previous work. So I didn't have any actual data files from any of the Myers and De Beers papers or any of the other papers. We just had images. So I guessed where they had taken their profile, and I extracted a data profile. And of course, there's more data now than there was back in 1987. And I created my own model that used this model of Myers and De Beers of the dipping sheets. I used our density values for the crust, slightly higher because I was including the lower crust, and an average Bushveld that we had measured, and a value for the mantle. So Myers and De Beers went down to about 15 kilometers. I went all the way down to the Moho because I wanted to investigate crustal flexure. Now with this kind of model, some of the work Tony Watts has done has shown that if you have something that's about 50 kilometers across, well, if it's less than 100 kilometers across, the strength of the crust, especially the continental crust, will support it. It will not bend the crust. It has to be larger than that to bend the crust. So there's no flexure with this kind of model because our weight our intrusion here is not big enough to actually cause flexure. And so then I said, well, let's make sure that what Cousins modeled is correct. You know, did he do calculations correct? And sure enough, here's my observed data going from west to east in milligauss. And here is the calculated response of this very simplistic Bushveld. It's, you know, literally in Gordon's program with about 8 corners and the density again that we measured. And here's the mantle flat lying. Now we have a load in the crust that is extending for 400 kilometers. This is heavy enough to cause crustal flexure. So without worrying about too many details, I allowed the crust to flex underneath. So now what we've done is we've taken this crustal density of 2.7 and pushed it down into the mantle. We have displaced the higher density mantle with lower density crust, and look at that. It brings those calculated values down to be a very good first order match to the observed data. So this very simplistic model shows the value of testing ideas with gravity. We now can say it is possible to have a connected Bushveld if we allow for crustal flexure. It also is one of the most powerful scientific concepts because we've made a prediction. We've said that the crust will be thicker underneath the center of the Bushveld complex. Keep in mind, this is at exactly the same time that we have 82 seismometers out throughout South Africa, and we are actually measuring crustal thickness with receiver functions, which Ray talked about in his last 2 talks. So we made a prediction, and I can tell you, I've never been so nervous until I saw those data come in. So the idea is that due to the strength of the crust, flexure will only occur if the Bushveld is large enough, if it's greater than 100 kilometers across. We've actually got an experiment in South Africa that demonstrates this. Why? Because the Trompsberg is an example of an intrusion that is supported by crustal strength. Remember when we looked at the gravity data in the beginning of this section, we said, oh my gosh, the Trompsberg has a larger gravity signal than the Bushveld. And the reason is the crust, the moho, we suspect, is not deflected at all beneath Trompsberg. Whereas here, this is creating a very long wavelength gravity low that combined with the gravity high here gives us this calculated anomaly. So Trompsberg's an example of an intrusion that is largely supported by crustal strength. A lot of people don't believe me, or our group that is working on this connectivity. There's a lot of dissent in amongst the geologists, amongst some fairly well-known geologists. Roger Schoon, who's a fairly prolific writer, and he argues with me every time he sees me. And so it's you know, this is from July 2009, but he's said it to me very recently. He thinks the western and eastern lobe are widely separated chambers that are unlikely to be interconnected. And he will say this over and over again. There was a more recent paper by Hans Taibo and Irina Artemeva and other co-authors in tectonophysics that suggests the crustal root may have deflected rising magma sidewards, leading to the formation of the 2 lobes of the Bushveld complex. And they repeated this again in 2015. So they are also saying that the 2 lobes of the Bushveld complex are not connected at depth, and that as rising magma came up, it was deflected sideways, and you have 2 separated intrusions. Well, what did the seismological data say? Steph, I'll finish this section in about 5 minutes. What did the seismological data say? Well, here are the stations of the Cap Fall project. These little dots that I've got over here, the yellow dots were the backbone of the seismic array and stayed out for the entire 2-year period. The blue dots were 1-year stations, and then they were moved to occupy the locations in the red. And this is just a small portion of the total array, but it gives you an idea of the context of the Bushveld complex. Okay, and so we are especially interested in stations 47 and 48. Here I've plotted the gravity data with the scale over here in milligauss and our east-west profile through here. We also have a worldwide seismological network. Lobotsi station is shown here, which is the data were included in this study. So here are the stations plotted along this profile, which so nicely cross-cuts the Bushveld. And this is the gravity signature going across that. And so we have this little gravity high here, which is in the far western lobe. We go north of the Pilansberg. So we have Bushveld complex here. We have this little hump in the middle, and then this little hook, and then another big portion of the outcropping Bushveld complex over on the right. And then we get this strong effect as we approach Mozambique. And here were the results. These were the initial results coming out from Teresa and Guri's work on the crustal thickness beneath the Bushveld complex. And here you can see it in profile. And here we see the first map that we made of the crustal thickness under the Bushveld complex. And interestingly, the station far to the north, that's, I forget that number, yeah, station number 51, was also showing quite thick crust. And so these are the data that were used in the GRL paper where Teresa's first author. And I used this diagram in the paper we wrote for SAJG on the connectivity of the Bushveld. And further, actually, Ray actually spoke about this project where Eldridge Kaswani and everyone else worked on the shear wave velocity structure of the Bushveld and concluded, as I understood it, that there are upper crustal layers beneath the center of the Bushveld with shear wave velocities high enough to indicate the presence of mafic lithologies. So we don't have the resolution with that particular method to really determine the thickness or the exact location of this layer, but at least there seems to be some evidence from this paper that it's there. So now we have new data. Nobody can model the Bushveld complex without accounting for the fact that we have crustal thickness variations. That must be incorporated into any model of the Bushveld complex we do. So I then produced this model, which is a little bit more detailed than just our very simple lopolith, where I've incorporated the outcropping geology. I've got the dips correct. I've got the location of the Crocodile River Dome and the Marble Hall Dome. All of the outcrops here are correct. And we can fit the gravity data beautifully. And in fact, we understand why this little hook is here because we actually have this disruption at the Marble Hall Dome. And we can now look at also some other evidence. We've got the Moloto borehole, which goes directly into mafic rocks. It's quite a ways in from the outcrop. So we have Moloto borehole, which is documented mafic rocks. And we have this interesting little piece here. Most people are familiar with the Palmate-Fontaine kimberlite, which is located over here in the Pilansberg complex. But the Palmate-Gott kimberlite is in the middle of the Bushveld. Look how central that is. Here's the western limb, here's the eastern limb. If you wanted to drill a borehole to test if the Bushveld complex was connected, you'd probably put it right where the Palmate-Gott kimberlite is. And so that's a perfect test. And what we did is we went to the Palmate-Gott kimberlite, which at that time had been mined to a depth of 30 meters. And they were in hard rock kimberlite. The wall rock is, of course, Karoo. And the xenoliths, the crustal xenoliths, were sandstones and lavas of the Karoo. But we found Bushveld xenoliths. We actually found hand samples of the Bushveld in this kimberlite material. So we're essentially using kimberlite as a borehole through the crust to sample for us what's underneath that kimberlite. And this is what it looked like when we went there at that time. It's a very small kimberlite, only 150 meters across. It's actually a series of 6 kimberlites. And here we are looking through the waste. We found a lot of interesting things in the waste, but the main thing we found were these little samples. And these look exactly like the critical zone of the Bushveld complex. And in fact, they are, they've got the exact same composition as rocks in the critical zone. They look exactly like thin sections from the critical zone. And so we think those are critical zone. And so now I'm moving into some of the 3D modeling that Janine Cole and Carol Finn have been working on. Janine is using Pygmy, which is a freeware program for 3D modeling of gravity data written in Python, which is really powerful. And I just want to point out this feature sticking down deep, deep, deep into the crust, which we think is the feeder zone near Potgietersrus. You may remember that was where the highest gravity values are. And we simply cannot get rid of that feature. And we have to accept that that is probably one of the main feeder zones for the Bushveld complex. So this is just another view of one of her 3D models. And I think I'll leave it there because I'm going to go way over time if I don't stop. So if I can have next week also, that would be great. And we can continue on. I know I didn't think it would take this long.